Figure 1 shows how 25 people travel to work. Their travel to work is represented by the events B, T, and W for bicycle, train, and walk. Part A asks us to write down two of these events that are mutually exclusive and give the reason for the answer. Remember, two events are mutually exclusive if they can't both happen at the same time. In the case of a Venn diagram, that's indicated where two circles do not overlap. In this case, if we looked at W and T, they don't overlap, so they are mutually exclusive. So walking and taking the train are considered to be mutually exclusive. Similarly, walking and bicycling are also mutually exclusive. Part B asks us to determine whether or not B, bicycling, and T, the train, are independent events. Remember that independent events are events in which the occurrence of one event doesn't influence the probability of the other happening. So the probability that somebody takes a bicycle doesn't affect the probability that somebody takes the train. So we can say that they are independent events. Part C says, one person is chosen at random. Find the probability that this person, first of all, walks to work. So if we look at our sample space, our total sample space is 6 plus 4 plus 5 plus 3 plus 7, which is equal to 25. Now we need to look at the number of people that walk to work. The number of people who walk to work are in the W circle, so the probability that somebody walks is equal to 7 out of 25, because there are 7 people there out of a total sample space of 25. Question D says, what is the probability that this person travels to work by bicycle and train? So we're looking for the probability that they take the bicycle and they sometimes take the train. So first we want to figure out how many people are in that intersection. So the number of people who take the bicycle and take the train are the intersection between those two spaces, which is 5 people. So the probability of B intersection T is equal to 5 out of 25, or 1 out of 5. Question 2 says, the following shows the results of a survey on the types of exercise taken by a group of 100 people. Complete the Venn diagram to represent this data. So our sample space is going to be 100 people. The first thing I'm going to look for is where all 3 of them intersect. In this case, it says that somebody does all 3. And we've got a little bit of a tabbing issue here. So it says 25 people do all 3. So that means right in the middle is where we'll put the 25. We know that in total, we have 65 people who run. We have 48 people who swim. And we have 60 who cycle. So we'll add that to the chart as well. Taking that piece and that piece and that piece of data. Now we're going to look at the 40 people who run and swim. The key word in there is and. So they do both. Another way of thinking of that, that's the intersection between running and swimming. So that is the space here between running and swimming. Now we've already got 25 people in that area. So if we've got 25 there already, that means the remainder in that space is going to be 15. 15 and 25 gives us 40. Now we can look at 30 swim and cycle. Following a similar approach, we look at swimming and cycling. So those are the two areas we're looking at. But then again, we're looking at an and. So it's the intersection between those two areas. We're told that there are 30 people who do both swimming and cycling. We've already allocated 25 of them into that space. So we only need to put 5 more in the intersection. Finally, we have 35 that run and cycle. So we're looking at the space, the intersection between running and cycling. We're told that there are 35 people that need to fit in that space. We've already got 25 in the center, so we need to add another 10. Once we've got those spaces filled in, we can go ahead and start to figure out what the remaining balance is. Let's start off with swimming. So it says we've got 48 people who swim in total. Right now, we've got 5 and 25 and 15, so that gives us a total of 45. So there are only 3 more that are in just the swimming category. Following a similar approach for cycling, we've got 10 and 25 and 5 for a total of 40. And we see that we've got a total of 60 that need to be in the cycling category. So we can do the math to say there are 20 that are just cyclists. And looking finally, running has to be 65. We've currently got 15, 25, and 10 for a total of 50. To get to 65, we need to add another 15. With that, we've now completed all of the circles, but now we need to do one final check to make sure that we've met our requirement to have a sample space of 100. To do that, we're going to add up everything that's in our sample space that's so far defined. 15, 15, 30, 55, 65, 68, 73, 93. We've got 93 in total, so that means there are 7 that are left outside of all the other samples that we've chosen. That gives us our complete Venn diagram for this data. Now we're asked to find the probability that a randomly selected person from the survey takes none of these types of exercises. So the probability that they do none of them, that is our group of 7 people over here. So the probability of somebody doing none is equal to 7 out of 100. C asks us what is the probability that they swim but don't run. So we're looking at the swimming category here, but we want to find just the people who swim but don't run. So they have to be outside the running area, but still in the swimming area. So we have to stay outside of run. So that's everybody in this region, which we can clearly see is 8, 3 plus 5. So the probability of swim, not run, or another way of saying that would be to say the probability of swim intersecting with the complement of run, which is equal to 8 out of 100, which can be reduced down to 2 out of 25. Part D says what is the probability that somebody takes at least 2 of these types of exercises. So if you think about this, what we're really asking is what is the probability that somebody falls into the intersection between running and cycling, the intersection between running and swimming, or the intersection between swimming and cycling. In each of those circumstances, those people take at least 2 activities. To write that out in notation, we'd say the probability, we're going to have a big bracket here, of A intersection B plus B intersection C plus A intersection C. Now that's the starting point. But one of the things you'll notice when we did this, each time we highlighted an area, we went back over the center region again where the 25 was. So in fact, by doing the intersection of running and cycling, and the intersection of swimming and cycling, and the intersection of swimming and running, we've included those people in the center 3 times. So in fact, since we've included them 3 times with those intersections, we need to remove 2 of them, because those people can only be counted once. So in addition to all of this, we're now going to subtract 2 times the intersection of A, B, intersection C. Now we need to see, looking at each of these intersections, what do they add up to as far as actual numbers of people. So if we take A intersection B, in that case we'd say it's the intersection between running and swimming, and there are 40 people that fit into that category. Then we look at the intersection between B and C, which we'll say is the intersection between swimming and cycling, which is 30 people. Then we look at the intersection between A and C, or the intersection between running and cycling, which is 35 people. Then we want to subtract 2 times the intersection of A and B and C, which is the spot right in the middle, minus 2 times 25. That's all going to be divided by the total number of people in the sample space, which is 100. When we add it all up, we get 40 plus 30 plus 35 gives us 105, and then we subtract 50 from that, we get 55. So we end up with 55 divided by 100. So the probability that somebody does at least 2 of these exercise types is 55 out of 100, or 55%. The Venn diagram in Figure 2 shows the number of students in class who read any of 3 popular magazines, A, B, and C. One of these students is selected at random. Show that the probability that the student reads more than one magazine is 1 out of 6. So the first thing I want to do is identify the size of the sample space. So our omega, and we'll add up each of the numbers, 10, 4, 2, 5, 3, and 6. We add them all together, and we get 30. In order to find the probability that somebody reads 2 magazines, we're looking for the intersections of magazines in the Venn diagram. At the moment, we're just looking at the number of students that read 2 magazines. So we're looking at A intersection B, and the number of students there is, this intersection point is 2. The number of students who read both B and C is 3. So the total number of students who read 2 magazines is 5. The sample space we said is 30. So the probability that somebody reads 2 magazines, is equal to 5 divided by the total sample space, which is 30, or 1 out of 6. Part B. Find the probability that the student reads A or B or both. So we're looking for all the students who read A, or they read B, or they might happen to read both. So we're looking at everybody that falls within the yellow space. If we add up the number of those students, we've got 4 plus 2 plus 5 plus 3 for a total of 14 students. This would also be expressed as the probability of A union with B, because what we just described there, of everything that's in A or it's in B, is the union. So the probability of A union B is 14 out of the total sample space of 30, which can also be reduced down to 7 out of 15. Part C. Write down the probability that the student reads both A and C. In asking that question, what we're looking for is the probability of A intersection C. If we look closely at the diagram, we can see that A and C don't intersect. There are no students who read both A and C magazines. As a result, the probability of A intersection C is in fact 0. So there are no students that read both. In question 4, there are 180 students at a college following a general course in computing. Students on this course can choose to take up to 3 extra options. The 3 extra options are system support, developing software, and networking. We're given the details on how things break out in who's taking which additional courses. So the first thing I'm going to do is look at the ones where they give us just sort of the core details, like there are 112 that take system support. So I'll go ahead and write that in, put that on my graph so I can keep track of it. 70 take developing software, so there's 70 end up there. 81 take networking, 81 with networking. The next thing I look for is whether there are any directly in the center. So are there some that take all 3 options? When I look through the description, I can see here it says 4 take all 3 extra options. So I can go ahead and I can put that 4 right in the center. Next, I see that it says 35 take developing software and system support. The key word there is and. That tells us that we're talking about the intersection. So we've got developing software and system support. That intersection is there. If there are 35 originally and we've already got 4, that means the remaining number would be 31. Next, I look, it says 28 take networking and developing software. Again, the key word there is and. We're looking at an intersection again, and it's the intersection between networking and developing software. So that's right here, networking and developing software. We're talking about 28 people. We've already got 4, so the balance is 24. Finally, 40 takes system support and networking. Again, it's an and, so it's an intersection. And we're looking at the space between networking and system support. If there are 40 and we already have 4, the balance there will be 36. Now we have enough information to complete the Venn diagram. In developing software, we need to have a total of 70 people. We've currently got 31 and 24 and 4, which is a total of 59 people. So we need to add another 11 into that space to complete the count up to 70. Similarly, in system support, we want to hit 112. We've got 31 and 36 and 4, which is 71. So we need an additional 41 to complete that area. And finally, in networking, we want to end up with 81. We've got 24 and 36, which is 60, plus 4 is 64. So we have a balance of 17 more that need to fill in. With that, we've now completed all of the circles, but we need to do the check to make sure that we meet our requirement that we've accounted for 180 students at the college. So we want to define our sample space, knowing that it has to be 180. Now I want to check all of my numbers. So I'll start with 112. I need to have 112 system support people included within that circle. I've got 41 and 31 is 72, 108 and 4 makes 112. So I've got the right number there. In developing software, I need to have 70. I've got 31 and 24, which makes 55, 66, and 4 makes 70. In networking, I need to end up with 81. I've got 36 and 24, which makes 60, plus 17, which makes 77, plus 4, which makes 81. So I know that all of the spaces now are correctly defined. They have the right number of people in each of the segments of our Venn diagram. Now I just need to look at the total and compare it to what we should have in our sample space, which is 180 students. When I add up 41, 31, 11, 36, 4, 24, and 17, I end up with 164. I need to end up with 180, which tells me that I'm missing 16 people. Now, once I've completed the Venn diagram, I can go ahead and answer the probability questions that have been asked. The first question, part B, says what is the probability that none of the 3 extra options are chosen by a student? In that case, it's the number that's outside of each of the choices. So the probability that they choose none is equal to 16 divided by the total number of students, which is 180, and that can be reduced down to 4 out of 45. Part C asks, what's the probability of getting a student that chose only the networking option? In that case, we're looking at just these students that are only in the networking space. So the probability of networking only is equal to 17 out of 180. And that can't be reduced any further. A more formal way of writing that would be the probability of networking intersecting with the complement of system support intersecting with the complement of developing software. So remember, we're looking for this part, which is in the networking support, so it's that area, and wherever it intersects with everything that is outside of system support and also outside of developing software. So by saying it has to be outside of those two things, it eliminated those spaces from the diagram and left us just with this space, which is what we wanted.